All right, so if you're in person here, I did put quizzes out if you want to pick it up later, but you don't need to because I returned it through Gradescope and I just checked and almost everyone's looked at that, so that's really nice to see. So that's my general plan is to grade that stuff over the weekend, but the way I'm going to do that is I'll just take the hard copies, scan it before I leave, and I'm going to return it and grade everything through Gradescope. That's my goal. I just want to reduce handling of the papers and feel like I can do it quickly that way. So I don't know if people have questions about them. I just have the quiz up on the screen right now. If people want to ask any specific questions, most people did pretty well. I thought I tried to be kind of straightforward about it. Maybe I'll just at least show the conjugate one because there were some algebra issues with this one. And it was tricky. It was a tricky one, right? So first of all, notice that this is the conjugate that you should be thinking about. Right, so you just change the sign between the two terms. You're just changing the plus sign, right? The plus sign between the two. Excuse me, you're changing the minus to a plus. And when you move forward in this, you just need to distribute, right? So you FOIL, like it says right here. And when you end up foiling, it simplifies down to something that's nice, right? Like it simplifies down into just this. And then the t's cancel. And then you just get this. And then you can plug 0 in there. And I know it's kind of going off the screen here, but when you plug 0 in, you get this thing that's boxed in at the bottom that I can't touch because I'm touching the screen with my finger. So anyway, I gave most of the points there. If you knew the right idea and you wrote the right conjugate down, if the algebra went a little awry, depending on how far you got, might have lost a half point or a point or something. But for the most part, pretty nice. So I just wanted to show the algebra on that though. Questions at all about the quiz? Because in order for the limit to exist, we need this to be true. We need the left-hand limit and the right-hand limit to equal each other. It has nothing to do with the open part. It has to do with the fact that when you walk down this piece, you're approaching this spot. And when you walk down this piece, you're approaching this spot, right? So that's what these two things are saying. Right, so the numbers are, you're just approaching the different spot. Other questions at all? Let me bust open the chat here on this in case people have questions online. I do see you. Anything there? Any homework questions that you want to talk about? I did post the homework for next week. I think there's 2 assignments. I want to say there's 14 problems. If we just kind of pop over to the weekly schedule, this is for this week, so it's not current, but I just wanted to remind you we've got our test next week, right? We've got our test next Friday in person in here. And that homework is going to be on the test. So it's only, I tried to reduce the number and not make it too intense because we have that test. Any thoughts about homework or questions or anything before we look at a little bit of notes, and then we're going to do the quiz, or our next quiz at the end as well. Any questions at all? Anyone? Make sure my speakers are working. They sometimes don't. They are working. Great. All right, well, I'm going to pop over to the notes then and continue with rates of change. This is, this piece of the notes, wherever that just went. The piece of the notes we're on right now is really a very foundational part of calculus, but just mathematics in general. This kind of idea of rates of change is what lots of future classes are all built on. It's how we model things. It's how we get answers about our world. And so it's like really useful stuff, I would say. And just to kind of review where we were, right? We looked at the average rate of change, which was this slope kind of formula. Right, so this thing we looked at previously in the blue is just telling us the slope between 2 points. And what I ended with last time is, if we take this formula and we put a limit on it, so we do the limit as x approaches b, then it becomes the instantaneous rate of change, right? So that's where we finished right here, was this is the exact same thing we were just looking at right in the previous page, except now we have this limit part of it, right? And the idea is as x approaches b, the average rate of change becomes the instantaneous rate of change, right? So we're really trying to calculate this blue line right here that I'm kind of highlighting. That's the instantaneous rate of change, and we get at it using this idea of a limit. So that's where I left off. And what we want to start with today, I know I kind of jumped around a little bit, but I want to just go and redo this page and talk about an estimate because it's interesting, but not as useful, obviously, as the exact value. Okay, so what this is saying is we can approximate the limit, right? So there's an approximate equal sign right there. We can approximate the limit shown below by doing an average rate of change between two places and then averaging those two rates. So let's draw the picture again. I know that was confusing sounding. So let's draw that same picture. I'm just going to redraw this picture right up here. Not the exact picture, but the function at least. And again, we're interested in some point B. So let's just put that point right there. And we want to know the instantaneous rate of change there, which I will again just represent with that dotted line. Right, that's what we want. Oops. We want the slope of that line. Sorry, we don't want that line. We want the slope of that line because if you remember, it's like if we zoom really, really close to the function, it's like that's what's going on right at that function. It's telling us how it's increasing or decreasing. Okay, so we want the blue line, the slope of the blue line. And so what this method is saying is we can think of a couple points near B, right? We care about the point B, but we can look at a couple places near B that will actually allow us to estimate this. I'm actually just realizing too, what people are talking about looking at my screen here about the bottom getting cut off. The bottom gets cut off because of the bottom of this. How do you make this go away? Like on my screen that shows more stuff. Anyway, sorry, I just got distracted there. This is page 18. Yeah. Sorry about that, I got a little distracted. So what this formula is talking about is we can look at a place a little bit before A or B and a little bit after B. So let's label those places. Let's label A and C right there. Right, you can see it says B is between A and C right at the top there, right? And so what we're going to do is we're going to do the average rate of change from A to B, the average rate of change from B to C, and then we average those average rates, and that will approximate the middle one. So the idea is this, in other words. I'm going to get my line number, my lines out here. So here is f of A, and here is f of C, right? We're going to do a dotted line between each one of those points and the point we care about. So like this, in other words. I guess I should maybe use different colors here so that we can color code it a little bit. Come on. My goodness, I'm sorry, this is getting so jerky. I don't know why it's being so sensitive here. So what I'm trying to say is the green line is given by this piece. And the purple line is given by this piece, right? So we've got the second one right here, and the first one right here. See what I'm saying there? We're just doing the average rate of change a little bit before B, the average rate of change a little bit after B. So one of them's too big, one of them's too small, right? Like one's too steep, one's too flat. And then when we average the two of them, it gets like approximately right is the idea. Right, so we do, let me just maybe make a quick note of that on the side here. So what we're doing here in this method is it takes the average rate of change from f of A to f of B, so a little bit before B, and from f of B to f of C, and averages those rates. So again, it's just an approximation, right? So this is an idea of if we didn't know anything about limits and we didn't know the techniques we've been learning about, we could just approximate these things just by using average rate. So people get what I'm kind of seeing there. I know it's a little bit of a jumbled thing. Try my best. Thoughts? Questions? What do you think about that? Anyone online have anything to add there? So how do we get a good approximation? Right. In other words, how do we choose A and C? We know point B. B is the point we care about. But how do we choose points around B to get a good approximation? Thoughts about that? There's a couple of things that would like ensure we get a good approximation. What do you think? Yeah, we want to get like close to B. We don't want them to be way, way far away because then the function might do other dippy things, right? So no, closer to B, the better. So the closer A and C are to B, the better the approximation. I'll just note too that you want to do like an equal interval on either side too. Maybe that's obvious, but you don't want to do like 2 away from it on one side and only 1 away from it on the other side because that's going to be a little wonky. You want to be like an equal interval around B. But otherwise, it's pretty arbitrary. And in the homework, it tries to get you to pick specific numbers. It gives you like tables and stuff to pick numbers out of. But if on a test or in practice in general, you just have to choose numbers close to B. That's sort of the idea. And I think maybe I should just clarify this even further because I haven't written it down. I have a note here about it. The blue line is what we care about, right? We care about the slope of the blue line, and that's what we're calculating here with the derivative. This is the slope of the blue line, and that's what we're trying to calculate. That's the whole goal here. We're trying to calculate. All right, that's it all. So we've got an approximation and we have an idea about how to do the exact value. And the next couple of pages are just a bunch of examples of doing those things. So are there questions about the concept at all before we look at that? So some of the ones I just mentioned, the ones in the homework, sometimes have a table, for example. So some of them look like this, where in this particular example, we're thinking about C being some concentration of drug in the bloodstream. Right, so I always do the example, oh, you have a headache, you take Advil, it takes a while to go into your bloodstream, right? And it's being measured in parts per million, and T is given in minutes, right? So you plug in a T, it tells you how much parts per million is in your blood. And this question wants us to estimate specifically the instantaneous rate of change at 0.2, right? So this is the one we care about. We care about this moment, but we're going to estimate it by looking a little bit before that point and a little bit after that point, right? So we're going to do this idea that we just talked about. We're going to pick a B or an A and a C and estimate it, right? So let's look at like color coded again. We'll look at the average rate of change from here to here, and then we'll look at it from here to here, and I'll use those 2 colors, and then we'll take the average of those 2 things. Okay, so let's see. So the derivative C prime at 0.2 is approximately, right? This is the squiggly equal sign is important. It's showing that we're not being exact. We're approximating this. And I'm going to use the formula above there. So it's 1/2. Let me start using my color codes here. Oh, I'm not going to easily be able to get into that color code. How do I get another color? Maybe this one. Right, so that's the blue part. That's the blue. This is supposed to correspond to this thing, right? And then we would add to it the other one, which is given in green. So if you just look at the formula right at the top there, it's exactly what we're doing, right? We're looking at the average rate of change a little bit before the point we care about, which is 0.2, a little bit after the point we care about, and then the 1/2 is averaging them, right? This 1/2 right here that I'm circling, that's averaging those two things, right? When you add two things together and then divide by 2, it's averaging it. Thoughts about that setup? We'll just make another quick note in case this isn't clear, in case someone's lost but doesn't want to say anything, right? This is the average rate of change from 0.1 to 0.2, and this from 0.2 to 0.3. Anything? Seems okay? And if we had a function, we'd plug the numbers in and get those values, but it's just a table, and so we can just pick those values right out. So we don't even have to like calculate anything, we just have to pull them right out of the table. Let me switch over to black ink here and finish it off here. So this is 1/2 0.94 minus 0.89 0.1. I'm just pulling these numbers right out of the table. Something's not right here. No, that's right. Yep. And just calculate it, right? Really easy to do. We get 0.45. What are the units? Forgot to write my units in there. Thoughts about that? We've got parts per million on the top. On the bottom, we have time. I guess technically minutes. Yep, go ahead. Nice. ppm per min. That's our takeaway. What does that mean? That's the whole point here, right? We want to like learn something about what this is saying. Yeah, as a minute goes by at this rate, 0.45 ppm would enter your bloodstream. But notice that, just kind of looking back up at the curve here, it would be like we just calculated the slope of this blue line, right? But that slope only exists at that very, very point. And as soon as you step right to the right of that, like here, for example, it's going to have a different slope. And so that 0.4 ppm is highly localized. And so, you know, when John says after 1 minute, 0.45 will enter your bloodstream, that's if it was going to stay at that rate, right? And so, in other words, we wouldn't want to assume that a minute later it would go up by 0.45, but that's like a good estimate about what might happen. Right? Does that make sense? It's like we're going up this way. It's like you're walking up a hill with your eyes closed, right? You know how steep you are right now, but when you take that next step, you don't know if it's going to be the exact same steepness again, right? It might go down, it might go up. You don't exactly know, but it's a good estimate. You're kind of at this steepness, right? And you take a step, it's probably going to be the same, about the same steepness later if you take a small one. Anyway, one way to think about it. So I was just going to write that down because we do want to interpret this stuff. So this is, oops. This is telling us, and there's a positive number too, which means it's going up, right? Of course. So we're still ingesting it. So at 0.2 minutes, the concentration is increasing by 0.45 ppm per minute. And I just can't say it enough times that because that unit is a little bit misleading. ppm per minute. It makes you think like, well, next minute is definitely going to go up 0.45. Just saying at this current rate, that's what would happen. All right. Is that okay? The estimate part, the estimate. Yeah, let me just let people finish catching up here. See if there's anything in the chat. Like it. Concentration. Yeah, I don't know if you guys ever use these Apple pencils. They're pretty amazing. I always avoided styluses. They're really nice, but I'm still figuring out how to exactly use it. Believe it or not, I think it actually improves my handwriting, if you can imagine. That's how bad my handwriting is. But I think my handwriting is kind of jerky in general, and it kind of like smooths it out a little bit. That's kind of funny. Not that it's good by any means, but anyway. Other questions? Okay. Okay. Yeah, sorry. Yeah, so this, we didn't use this piece at all, the 0 component, because we picked an interval 0.1 on either side of it, right? So it didn't come into play. If we wanted to use that one, we would probably want this one on the right then, so we'd have an equal interval. Yeah. But since we had these two pieces that were really, really close, it just made sense to get as close as possible and then use those, right? Yeah. Yep, good thought there. Other thoughts? Someone said, why is there a 1/2 in front of the equation? Because what we're doing here, this is kind of the best way to think about it. We're taking the average rate of change from two places, right? One's too big, one's too small, and then we average those two things. And so when you have two numbers and you want to average them, you add them together and divide by 2. So that's what's going on here. You add them together, 1, 2, divide by 2, and then you average that. It's kind of confusing when it looks like this, because this is a compound fraction, right? It's like a fraction inside a fraction thing. And so we can just take the 2, dividing by 2 is the same thing as multiplying by 1/2. And so it's just a way to simplify that down and make it not a compound fraction. That makes sense, Sebastian?
So then what's it called? Are we taking the number that we got from the top, like the 0.94 minus the 0.89 and all that? We're doing that. And then when we get that and we divide it by the 0.1 that we have right there, we get that number. And then we take that number divided by half.
So yeah, you do this, the thing I'm doing in green.
Yeah, we
You
get
get a number out of that, and then you either divide it by 2 or multiply by 1/2, which is the same thing. Multiplying by 1/2 is the same thing as dividing by 2.
Cool. Thank you.
Other questions? Yeah, thank you for clarifying that. Anything else? Keep them coming. Nothing else in the chat. Okay. So did we look at that one before? I think we did, right? So we looked at this Kingfisher example previously, where we were looking at the average rate of change of this fish or this bird diving into the water. And we're going to revisit the same function, but think about the instantaneous rate of change, right? So on this thing that I'm showing right here, this one at the bottom of the page, we just said that the average rate of change was 10 feet per second downwards. It was negative. And now what we're looking at is we're going to hone in on a specific location on the graph and think about what the slope of the tangent line is, right? So it's a different look at the same function, is what I'm trying to say. All right, so we're going to estimate the velocity of t equals 1. So let's just go back to the graph real quick. T equals 1 is right here. And so we're looking at this part of the graph, and we want to estimate this right here. In fact, is that graph on the other page? Why do I keep going back here? Put that down here. I should have. Maybe there's room. Okay. So we're going to estimate it and then calculate it exactly. I would actually like you to take a second and think about what the estimate would look like. So we're going to do this exact same thing again that we just did a second ago, just right down here, except instead of pulling the values out of a table, we have a function to plug numbers into. And if we want to look at t equals 1, we need to choose some points around 1 to look at. So maybe we could all just get on the same page and think about what that might be. Maybe I'll just write something down and let you think about it for a second. So what we want to do here in A, and try not to write too big here because we have a lot more to write down below there. We want to estimate the derivative at 1. That's what A is telling us to do. And we're going to approximate it in part A by doing that formula we just did. And so let's look at the average rate of change. Let's go from 0 to 1. And let's go from 1 to 2. So I'd like to just take a second and just let you at least try to write down the formula of what that would look like. If you know, if you don't have a calculator, this one actually isn't too hard to plug numbers into. At least if you can get the next step, like what does the function value look like? This equals 1/2 of what? Let's just spend a few minutes on that. It's good, helpful to think through this while I'm here, and we can clarify any misconceptions. Make that bigger too. Is that helpful? No. There we go. My normal classes, this is when I put on music. Josh was talking about that. I love throwing some music on in this, but just not there yet. Can't figure it out. I just hate the silence. I hate the awkwardness. All right, I'm gonna slowly write down the next step and let me know what you think. Does that look okay so far? These values I'm showing, h of 1 minus h of 0 over 1 minus 0, right? This is the average rate of change from 1 to 0, or 0 to 1, and then from 1 to 2. And we're just going to take these things and we need to use this function to plug them into, right? So h of 1 is plugging a 1 in, right? H of 0 is plugging a 0 in. H of 2 is plugging a 2 in. And we just get numbers out and it falls out kind of easily. That seem okay? All right, let's go ahead and finish this one off then. So I plugged the numbers in. This one's not that hard to plug numbers into, but I did it ahead of time. When you plug a 1 in, you get 14. When you plug a 0 in, you get 20. So that's minus. And then 2 minus 1 is 1. And then when you plug a 2 in, what did I get? I got 0 minus 14. Super easy to calculate, right? Oh, let's add the units. Let's not forget about that. So the units here are feet on the top and seconds on the bottom. So our final units will be feet per second, right? So just helpful to kind of note that early on. And so we get a nice easy answer. This turns out to be 1/2 minus 6 minus 14 minus 10 again. And I'll just remind you, it's negative because the bird's going down. And it just happened to be the same as it was last time. It was total coincidence. Usually not the case. It's actually it's funny. It's an application of the mean value theorem, I think. Sometimes we get to that. I have to remember this for later. That's about the estimate. Just an estimate.
Can you repeat that, please?
Sure. So we were estimating the average velocity on this one. And so we were looking a little bit before the point we cared about and a little after the point we cared about. So we care about the point t equals 1. So that's why we looked at from 0 to 1 and then from 1 to 2. right? So if the point we care about is 1, we will look a little bit before it and a little bit after it. Right, we cared about this point. And so that's why we did 0 to 1, 1 to 2. Even better would have been like 0.5 to 1, 1 to 1.5, right? If you kind of squeeze in on 1, you get a better estimate. But then you have to plug fractions in. So we were trying to avoid that. So anyway, that's why I chose those two intervals. And so then the first one, this, right? This is just this average rate of change. And this one is just that average rate of change. And then we just plug the numbers into the formula to get these numbers. So like 14, for example, was h of 1. And 20 was h of 0, etc. Oops. Does that clarify a little for you? Is that the sort of thing you're hoping for? I'll assume that was a big resounding yes, unless you say otherwise. All right. What we really care about is the exact value, which is more important for sure. There'll be questions like this one. There'll be questions to estimate it. I'll put a question on the test that asks you to estimate it for sure. But what we really care about is this exact value, doing this thing in the box. Right? This is the thing that we've been building up to it. It uses limits. We're going to use the things we practice, the techniques, and we get the exact value of the instantaneous rate of change. So this is really what we want to do. So let's do the exact same thing here, except we'll calculate the value exactly using the exact limit definition. And we need a little bit more space for that because it's usually a little bit more involved. So part B would be doing the limit definition. So I'm just going to write the thing. I'm just going to copy this thing down, right down below in this context. So we care about the point 1, right? So we're going to do h prime of 1 is the limit as t is approaching 1, because that's, again, the point we care about is 1. And so then it becomes this. All right, so what I'm trying to say here is in the above definition, the b is 1. Right. That setup seem okay? All I've done is just plug a 1 into the above formula. All right, so let's just start plugging stuff in, right? So, and I mentioned this last time, but I'll just remind you again up here, right? I said all this stuff last time over here on the right. The f of x is just going to be the function. X is just a variable. In this case, it's a t. These two things, which are these two things, those are numbers. So f of b is b plugged into the function, right? And b is just the number. So the things on the right are going to be numbers. The things on the left are going to have variables. And so let's do it. All right, so h of t is just the thing right here, right? This is h of t. And so that's going to go right into the h of t spot. Right? And so that's going to be this then. And then h of 1, we just found out from the previous thing, when you plug a 1 in there, we got what, 14. Except I forgot to write the limit, so I'm going to have to slide this over in a second. Going to move, oh no, I snagged that other thing. I forgot to write the limit in there, that's why I'm sliding this over.
When you move it over there, I can't really see it.
What's that?
Still can't really see it.
Are you using a computer?
Yeah,
Are you in full screen mode?
yeah.
How's that? I don't want to get too small here.
It's okay.
Okay. let me also just try to label this. I should have done this previously too. If I slide this down. Right, this is the h of t. This is the h of 1. What do you think? This is usually the part where people get a little confused. Seem okay? Because if that makes sense, at this point, we're just doing the things that we know how to do, right? It's going to be indeterminate. We're going to factor and cancel. We know how to do this from now. So thoughts? Seems okay? All right, let's just do it then. So let's just keep going. And we just simplify things down, like I said, and we'll use the techniques that we learned, et cetera, et cetera. So this is the limit as t goes to 1. So just do 20 minus 14 to get the next step. 20 minus 14 is 6. And it's indeterminate. You can double check that, but if you plug a 1 in there, on the bottom, you clearly get 0, and then the top, you'll get minus 4, minus 2, plus 6, right? So that's going to be 0 over 0. Doing good on room here, doing okay on room. And so we should factor and cancel this one. And I hope that's not super surprising to people, right? There aren't tons of options. We're either combining, conjugate, et cetera, et cetera. The only one that applies here is factor and cancel. We need to start feeling kind of comfortable with that. So let's do that then. Let's factor this one. It's kind of tricky to factor, right? But I know that the whole point of factoring is to cancel out the denominator. So I know that one of the factors is going to be t minus 1. It's because we're in a math class and I know that that's going to happen. This isn't a real world application where maybe this wouldn't work. It's going to work. And so that just gives you a hint about how to proceed, right? And that would help you realize that it factors into this other piece. It's kind of hard to get the 4t minus 6. It's not impossible. It would take a little bit of thought. But if you know one of the factors is t minus 1, that should happen pretty easily, right? And that was nice because the t minus 1s just cancel. That was the whole point. I can't stress that enough. That's how we knew that that would be the factor. And so now we can plug a 1 in. And you can plug a 1 into minus 4t minus 6, no problem. That's minus 4 times 1 minus 6, again, is minus 10 feet per second. I'll just add the note at the bottom. It's kind of an important note. The 3 times we've looked at this function, we got minus 10 every time. Total coincidence. And I always go back and forth about whether I should just come up with another example so that they're different. But I like this example. So I'm just going to make this note. So our estimates, let me write that over. So our estimates for the average rate of change, instantaneous rate of change, and the exact rate of change were all minus 10. This is a coincidence. I just don't want you to think like you should always get that. It's a coincidence. I don't know. Just don't expect it all to happen. Sorry, that went off page a little bit. There you go. There's no, should be an N in there. Coincidence. Is that how you spell coincidence? No clue. How are we doing here? I'm pretty good. On the next page, yeah. Okay. What? Oh, because they're all the same. Yeah. I mean, most of the time, I probably wouldn't give you one function and ask you to do the same thing, do it 3 times. So I'd probably split it up, and so you don't have that feeling. All right, thoughts at all about that? Oh, great on time. I think I would like to just look at the next page and then look at our quiz here. No questions? Is that the only example I do there? Yeah, so I would say this is the only exact example I do, but there's some on the homework for next week. So usually let, just like we've done in the past, let people look at the homework, maybe come up with a question that you want to look at, and we can look at some together Monday, Wednesday. Oh, we don't have class Monday, so Wednesday. I know class Monday because of the President's Day. President's Day, right? Some holiday. Okay, let's just tie this up, let's button it up and talk about what this looks like. We already kind of know what this looks like, right? So this page is all about visualizing rate of change, like you can see. We've already been kind of visualizing it with some of these graphs or some of these hypothetical images up here, right? But sometimes it's nice to put it all together in some summarizing picture. And so the three things at the top here, what we're kind of focusing on here, which is that if you have a positive rate of change, that means the graph is increasing. If you have a negative rate of change, that means the graph is decreasing, right? Because if it's the slope of the tangent line, it's going up, it's going to be positive, it's going down, it's negative. And moreover, a really, really big thing later in the course and just in calculus in general is thinking about where there's no rate of change. Where is the graph flat, right? So I like to talk about this in the context of a trip to Philadelphia. So let's say that the graph down here represents Philadelphia. I'm sorry, our trip to Philadelphia, we've got like Fitchburg down here at the bottom. And then we drive along the way, and then the end point here is like Philadelphia. So maybe Philadelphia is here. And so it's like the distance from Fitchburg is the y-axis. So if that's a distance from Fitchburg, it's like we started going towards Philadelphia. We got like most of the way there, and then we turned around because we forgot something at home or something. I don't know. We left something at the gas station that was in, where is that? That's like Worcester or something. And then we had to go all the way back, right? So we got closer, we turned around, and then we went back. And so there's some questions at the bottom here, just kind of help us think about this situation. So let me go ahead and label a few points, and then let's talk about those points. So let's label this point right here, A. And let's say this is the point 2. Let's make B right below that peak, okay? C is going to be right in the middle there. D is going to be right here. And then let's just leave it like that. Okay. So thoughts about where the rate of change is the largest, right? That's the first question. Where is the rate of change in this picture the largest? Or what does that mean? How do we know what's the largest?
Where it's the highest?
Yeah, so 2 answers. I heard, I think it was Janetta say where it's the highest. And what did you say, John? And then John saying is where it's the steepest, right? So if we're thinking about the rate of change, maybe we should just write this. Rate of change equals the steepness of the graph. Right? It's the slope of the tangent line. And so if we want to know where it's the biggest, we'd be looking for the place where the graph is the steepest. So where is that?
Where I'd say B.
So this is pretty steep here from A to B, but I would argue that this one over here is actually steeper on the right. Right? If we look at this point right here, like this section of the graph, let's label this, let's star it right here. I think the star is the biggest part because the graph is the steepest. And so someone has said a couple times, I think someone remotely was kind of repeating that maybe they think that B, this location, is the biggest rate of change. That is one of the highest points on the graph, but it's actually flat there, right? And in other words, the slope of the tangent line, if we drew the tangent line, it would look like this. That has a slope of 0. And so B, in terms of rate of change, actually has no rate of change. And so that's actually one of the answers to the next part. Right, this part right here, where is there 0 rate of change? The next question. That's going to be at the peaks. And so B is one of those. Let's maybe we'll star those with another color. Let me put a green star there, and a green star there. The green stars are where there's 0 rate of change. Right? The graph is flat there. In other words, the slope of the tangent line is 0. That's a really important point. Again, that's something where we hone in on once we look at derivatives a little bit more. We hone in on how do we find these maximum points? Because that's an interesting point. Those B and D is where we turned around, right? B is where we were driving towards Philadelphia. We forgot something. We turned around and started going back. We cared about our trip or whatever. We were trying to analyze the trip. That would be an important point, right? D is where we were heading back towards Fitchburg, and then we turned around and started driving back towards Philadelphia. So again, something changed there. There was some kind of event. So those are interesting points usually in functions. Questions about that 0, like what rate of change means? I feel like people are a little bit confusing it with biggest points on the graph. I'm talking about steepest or not steep. Thoughts? Seems okay? So I've already mentioned this. The next question is what's happening at number 3. Let's go ahead and label number 3. Let's say 3 was this section of the graph. What's happening there? I've already said it a couple of times, but just going back towards Fitchburg, right? And so the tangent lines are negative there. So direction matters again, just kind of emphasizing that. So 3 is going back towards Fitchburg. But the thing I really want to emphasize, that means negative rate of change because direction matters. All right, I forgot to add 0.4. So I'm going to add another dot on the line here. I'm going to put it right here. Everyone see this number 4? I'm kind of circling right now. I just added that dot there. Because the next question says, how do we draw a line whose slope is given by the average rate of change from 4 to 2? We've done that a bunch of times. Let's throw a line in there. Right, so the purple line here tells us the average rate of change. All right, the last 2 questions are also relevant for future, what we're doing in the future here. So the last 2 questions are, where is the graph slowing down? And where is the graph speeding up? I'm sorry, where is the car slowing down and where is the car speeding up? How can we tell if it's slowing down or speeding up? What do you think about that, John? Yeah, so again, when we're thinking about velocity or rates of change, we're thinking about the tangent line. So slowing down would mean the tangent lines are flattening, and speeding up means the tangent lines are becoming more steep, right? So slowing down would be somewhere between A and B, for example. And also from, say, C to D. Let me do this. So from A to B and C to D. And the way you think about that is because the tangent lines become flatter. So if we thought of the tangent line, let me kind of draw a couple tangent lines on here between A and B. Early on, it's kind of got this slope. As we get closer in B, it's flattening out, right? So it's decreasing. Similarly, if we went from C to D, C is like kind of going kind of fast towards D. But as we get closer to D, the tangent line flattens. Right, so the places where the tangent line's flattening is slowing down. And then speeding up the opposite. So it'd be like B to C or beyond D, for example. Right, so speeding up could be from B to C and beyond D. Because the tangent lines steepen. Let me try to make that a little more legible. Steepen, is that even a word? Let's just say become more steep. Right, the slopes are going up in a positive or negative way. Right, B to C, we're going faster, but we're going faster negatively, and beyond D, we're going faster, but we're going faster positively. I don't know if that. Yeah, I think I'm stopping there. Some questions? Anything? How are we doing here?
Did you decide where to put 2, 3, and 4? Did you just randomly pick, or was there a reason you put them in those spots?
2 and 4 were totally random. 3, I was just trying to illustrate what it means to go for the graph to go down. Just trying to illustrate a negative rate of change. So 2 and 4 were just random spots. 3 was trying to highlight the place where the graph is going down. Other questions? All right, for folks who are doing this remote, I'm going to get folks set up here with the quiz, and then I'll probably send the quiz in. I think I can just try to send it right into the chat here. Actually, I'd like people to turn their cameras on first. So if remote people get set up, turn your cameras on, etc. I'm going to get folks here set up with the quiz. Open notes. It looks exactly like the homework. I even took a question out of the homework itself. So if you brought your homework with you, I'm hoping to make this nice and easy. Actually, there are 2 of these questions from the homework. I think there might be. Yeah, let me get people set up in here, and then I'll come back and send the quiz through the chat there. All right, let me try it. Tayshawn, you there? You able to turn your camera on?
No, my laptop camera doesn't work.
You guys get that quiz through the chat?
I don't see it.
Nothing there. I don't know why that doesn't work. It gives you the option to send a file, and then it doesn't work. It's like the 5th time I've tried this, and it just doesn't work. All right, I'm gonna have to email it to you guys. Jayla, what's your email? Not oh, you got it, Jayla. Okay. I can't find your email, so you're all set. Okay. All right, I'm sending the quiz now.
My bad.
I'm gonna email it to you now, Sebastian.
So for the quiz, do you want us to do it on like some scrap paper and then take a picture of it and submit it, or how do we do this? Because I got the email for it, like I can see it, but like, what's up?
You want to do it on separate pieces of paper, scrap paper. Create a single PDF. Email me the PDF.
All right, come.
And you can use your notes for this.